Okay, so I will talk about, I would like to review some basic results. Oops. First of all, let's put the glass here. Okay, please. No, it's the other way. It was working before.
I know. I will do something else. Okay. So it is your lecture. Where is it on the which file? Okay.
This one.
We'll do something else. Okay. We will open it.
And it's just there too. It's okay.
It will work. Full screen mode. Voila.
Huh? Wow. Okay, thank you very much. I'm sorry. Yeah, sorry. Okay. So I want to review some basic results on determinantal variety and show how to use singularity theory to study the invariants in geometry. So I will talk about essentially isolated determinantal singularities, a little bit about singularity theory of matrices, and these other topics here are pupurri on invariants of determinantal varieties. So the subjects of the talk, they are related to results of 4 PhD theses that I mentioned there. So the thesis of Miriam Pereira was my student in 2010. The thesis of Brian Pike, Jean Damon's students in 2010. Bruna Orefsio Okamoto, student of Nuno Ballesteros and João Tomasella, and Nancy Chachapoya Siesken. She was a joint student of Jean-Paul Bracelet and myself. And my talk is also very much inspired on the paper of Ebelin and Guzenzat, 2009 paper of Ebelin and Guzenzat. Before I start, I would like to also quote these very recent and very interesting results on isolated determinantal singularities. So papers by Nuno Ballesteros, Okamoto and Tomasella, and Gaffney and Rangachov, and Anfribs Krieger and Matthias Zapp. Okay, so my viewpoint is in fact to describe some geometric constructions which are useful in the study of determinantal varieties, and they hold also in the non-isolated case. So let's start. So we first define a generic determinantal variety, which are the models determinantal variety in space of complex matrices. So let Mn be the set of all m by n matrices with complex centroids, and we denote by MMNT the set of all matrices with rank less than T. So this set is a singular variety called the generic determinantal variety. It has codimension n minus t plus 1, m minus t plus 1. Its singular set is also a determinantal variety, is mn t minus 1, and so on. So the singular set of mn t minus 1 is mn t minus 2, so that we obtain decomposition of the set mnt as the union of this strata, smooth strata, and this union is a Whitney stratification because in fact these strata are the orbits of the action of the linear group GLN cross GLM in this space. Okay, so a determinantal variety is in Cn, in one open set of Cn, is given in our contest by a map defined anew, taking values in the space of matrices, so that for each x we have f of x is a matrix, m by n matrix, and the coordinates of my matrix are analytic functions, right? So the determinantal variety of type MNT is just the pre-image of the generic determinantal variety MNT, as long as it has the right codimension, which is the codimension of MNT. Okay. So, for instance, if you have this map from C4 to the space of 2 by 3 matrix, then the F inverse of M232 is just the locus of the zero set of the 2 by 2 minors of the matrix. It is a surface in C4 with isolated singularity at the origin. Okay, so this condition here about the codimension, of course it says that generically F should be transverse to the strata of the stratification, right? Because of the codimension. So we want to work with a class of variety which is a little bit, satisfies a condition a little bit stronger. It was defined by Ebeling and Guzenzart, and it's this. So we say that given the germ of a determinantal variety, we say that 0 is an essentially isolated determinantal singularity at the origin if F is transverse to all the strata of the stratification away from the origin. So in a punctured neighborhood of the origin. Okay? So this transversality condition guarantees that the singular set of an essentially isolated determinantal singularity is again an essentially isolated determinantal singularity. Okay? So these are the objects I'm considering. So, for instance, complete intersection are EIDS of type 1 and 1. This example is a curve in C3, so it's just a triple point, right? And it's Cohen-Macaulay codimension 2 singularity, which is a general fact. By the Hilbert-Bush theorem, we have that all Cohen-Macaulay codimension 2 singularity can be represented by an n by n plus 1 matrices, as well as its deformation. So the deformation of a Cohen-Macaulay codimension 2 singularity can also be obtained by deforming the n by n plus 1 matrices. Okay? Okay. So what type of deformations we are considering in this talk? We are considering deformations that are deformations of the determinantal deformations of the same type. So, and in particular, I define a smoothing, essential smoothing of an essentially isolated determinantal singularity as a subvariety living in a neighborhood of the origin, which is obtained from a matrix which is a deformation of my original matrix given by F. Good? So deformations for me are deformations given by determinantal deformations of the same type. For instance, in the previous example, that in this case for A, B, and C generic, this gives me deformation, which gives me an essential smoothing of my curve, which is in fact a smoothing. Okay. So it's important to point here that essential smoothing is not necessarily smooth. It may have singularities. Okay. Okay. So a special class of determinantal singularities are the ones that have isolated singularity. So from the transversality, from basic transversality condition, we see that if n is less than or equal m minus t plus 2, n minus t plus 2, then the EIDS has isolated singularity, because this is the codimension of the singular set of MNT. Okay? And of course, if n is strictly less than MNT plus 2, NNT plus 2, n minus t plus 2, then X0 has a smoothing, because transversality to the singular set will be don't meet the singular set. Okay, it's not true that every determinant of variety with isolated singularity has smoothing, right? For instance, in this example, this simple example, in fact, for any greater than or equal to 6, we always have, is easy to see, that F is transverse to the strata of the stratification. And in particular, when n is equal to 6, the singularity is isolated, but because of the transversality, it's rigid. Okay, so it continues if we perturb the matrix. So the second part of my talk, very quickly, I would like to say that we can use singular theory of matrices to understand a little bit more what class of singularities we are dealing with. Okay, so the methods of singularity theory applies most to complex and real matrices, and I recall here that these are a list of papers in classification of singularities of matrices. So we have the paper by Arnold in 71 with about square matrices, and then a nice paper by Bruce in 2003 in which he classifies simple symmetric matrices, and he finds a very nice relation between the Trina number and the Milnor number for this class of matrices. In fact, he proves that they are equal in his classification list. And this factor was later proved in general by Gurionov and Mont in 2005. And I also remind this paper by Anne Friebs-Krieger and also the paper by Anne Friebs-Krieger and Reumer, in which they classify Cohen-Macaulay codimension to simple singularities. Okay. So my student Miriam Pereira, she studied singularity theory of general n plus m matrices, and I want to, the setup I will quickly now say is from her thesis. So we studied determinantal varieties, which are defined by Fs, which are transverse to the stratification in space of matrices away from the origin, right? So we can define a group acting on the maps, right, and obtain information about my determinantal variety from this action. So I define a group G acting on the space of maps. The group G is the direct, semi-direct product of R and H, where R is the group of germs of analytic diffeomorphisms in the source, and H is just the product of the invertible matrices with entries in ON, in the germs of analytic functions. So, the given two matrices F1 and F2, they are equivalent if there exists phi, R, and all, such that that condition holds. That means we have a change of coordinates in source and plus this action of the matrices. The nice feature of this equivalence relation is that the group leaves invariants the start of the stratification in space of matrices. Then if two F1 and F2 are equivalent, then the corresponding determinantal varieties are all isomorphic. All the collection of determinantal varieties are isomorphic. Okay? If you have any question, please. Okay, so then this group is a nice subgroup of the contact group, and we can apply methods of singularity theory to study the class of varieties I'm looking at. So I can look at local deformations of my singularity to, for instance, define the tangent space. And in using the tangent space, I can obtain the classical results in singularity theory. So, for instance, a map is stable if the tangent space contains all deformations of F. So, and of course, this condition holds if and only if F is transversal to the canonical stratification of Mn. Okay? So, we also can define finite determinacy. We can say that F is kg finitely determinate if for every g with the same k jet as F, we have that they are G equivalent. And we have this criterion of finite determinacy. So F is G finite determinate if and only if the Trina number of F is finite. So this normal space of the orbit of F is exactly the space of first order deformations of F. And the Trina number is its dimension. Okay? So, of course, if the Trina number is finite, my F has a versal deformation with number of parameters being the Trina number. And we also have a way to geometrically characterize this fact. So, in fact, my map F is finitely determinate if and only if it's for some representative, it's transverse to all the strata of the stratification away from the origin. So, okay, to conclude this part, we have a correspondence between G finitely determinacy and of F and the fact that X is an EIDS. Okay? And of course, a stable perturbation F tilde of F defines an essential smoothing of my variety. Okay? Okay, so so far. Okay, here I have one example. This example is the first normal form from the classification of Unfriebs-Krieger and Neumann. And so they correspond to these surfaces, which are given by the 2 by 2 minors of these matrices. We can compute So this is, it has Turina number k plus 1. We can compute this unfolding. And the singularity theory approach is, among other things, helps to do the calculations and to compute the smoothings of the singularity, the essential smoothing of the singularity. Okay. At this point, we get to the first conclusion of this talk, which is what we just discussed. Give us a geometric construction. So, in which sense? I start with an EIDS represented by F. I can construct its stable unfolding, right? So the stable unfolding of F gives me an IDS which can be seen as a flat family over X, right? So if I look at this diagram, so then I have F, I have the stable unfolding F tilde, which gives me this big X here, which is also an essentially isolated determinantal singularity living in Cn cross Cs in such a way that it defines a flat family whose whose special fiber is little x, and whose generic fiber is essential smoothing of little x, right? So a little bit more. So we have in here in the parameter space, I have the bifurcation set of F, and which is an analytic proper set. So in the complement of this set, the complement of this set is a connected set. So for any two values of the parameter, I obtain that the corresponding smoothings are of the same topological type. So I have a singular fibration associated to an EIDS. This is, we can summarize the main question in this theory as understanding the singular fibration. So the singular fiber is well defined. It's just the essential smoothing of X. It may be a very highly singular variety, right? And but anyway, invariants of this generic fiber gives me invariants of the original EIDS X. Okay. So this is a central point of the talk. Is the first geometric construction I would like to show you. So we can define topological invariants associated to the generic fiber. For instance, the Damon and Pike and Ebelin Buzenzart, they defined the singular vanishing Euler characteristic of X. Of course, is an invariant of X, which is the reduced Euler characteristic of the generic fiber. And Nuno Balesteiro, Okamoto, and Tomasella, just to use a slightly different notation, in the case that the variety has a smooth, in the case that the essential smooth is in fact a smooth. They denote like this. Okay. So another invariant, using the same setting, another invariant is the dipolar variety. So we recall that if we have an analytic variety of dimension D, the dipolar variety is not well defined. But I can use a method that was used by Terry Gaffney, for instance, his topology paper, to give the following definition. So suppose that we have then X, an EIDS, and P, a function defined in X with isolated singularity. So let me take the formation of my X, right? And take also in such a way that X is the generic, is the spatial fiber of X. And then I take a linear projection P, which is a deformation of my function, so that for all t different of 0, this function is a generic deformation of P. This means I want here that this generic deformation, on one hand, behaves well at the singularities of the fibers of X, which are singular, right? In the sense that the differential of P is non-zero on limits of tangent space to the singular set. And on the other hand, I want that P is a Morse function defined on the regular part of the fibers, right? So then I can compute the polar set, looking at the polar curve, in fact, looking at the projection to the plane, right? And the polar set is just given by the closure of the singular set of this map restricted to the regular part of X. So then the relative polar variety of X is just that denoted in this way is just the multiplicity of this polar curve. Of course, in general, my polar variety, my polar multiplicity depends on the data that I just gave, right? Depends on the choices of X and P. But in the case of an EIDS, as we have this singular well-defined fibration, it does not depend on X. It does not depend on P, but depends only on X and, I'm sorry, it does not depend on pi. It does not depend on pi. But it depends then only on X and P. Of course, if P is a generic embedding, then MD is an invariant of the EIDS that we denote by MD of X. Okay, you notice that here, this projection to the plane, sorry. So, as we have here a generic projection to the plane, in fact, when I restrict to the generic fiber, what I obtain here is a family of Morse functions in the regular part of X, right? So then it follows that, in fact, this invariant is the number of non-degenerate critical points of this function restricted to the essential smoothing of the variety. Okay. Okay, so now I get to the second construction. So the first construction was the existence of a singular fibration, uniquely determined for our class of varieties, for EIDS. The second construction is the Nash transformation. That was defined by Tessier. I think I just don't need to repeat, but just the notation, if X is a d-dimensional analytic complex variety, and this is the Grassmannian, I can look at the Gauss map restricted to the regular part of X, and then the Nash transformation is just the closure of this image of this map. So here's the definition, and we have here that the singular point of my Nash transformation is at a singular point. The fiber of my Nash transformation is just the set of xt such that x are the limits of sequence conversion to x, and t are the limits of the corresponding tangent spaces to these points. Okay, so very surprisingly, we have this result for the Nash transformation. I mean, this is a classical result, but for me it was very surprising to discover that the Nash transformation of the generic determinantal varieties are a resolution of these varieties. So they can be highly singular, but with only one Nash transformation, you get a resolution of the singularity, right? So using this approach, it's possible to pull back this construction that shows that this map is a resolution of the generic determinantal variety, and we can obtain the Nash transform of the EIDS as a fiber square, as in this diagram here. Fiber square of m hat tmn by x over mnt. So everything works well. We can see that everything works well at the points that f is transverse to the strata, right? So then we are able to really complete the diagram and obtain the Nash transform of x as exactly this fiber square in this diagram. Okay, so as I said, if you have transversal to the canonic stratification, then it's not difficult to see that x hat, which is the Nash transform of x, is a resolution of x. My student Nancy, she proved the following result, which is a slightly generalization of that. Even if the map is not transverse to all the strata, but if it's transverse to the limits of strata, to the stratification of the space of generic determinantal varieties, then the result's true. Okay? Okay. Of course, at this point, the following are two natural questions that we can ask. So, is it possible to use the Nash transform to resolve the singularities of the EIDS, right? Of course, we know from Spivakovsky result that if we do the normalized Nash blow-up, then we can do it. Right? The question is whether we can or cannot do this just with the iterate Nash blow-up. And the second question, which is also very, very interesting, is, so if you give a general EIDS, we don't know whether when we do the blow-up, we expect that we have singularities. So the question is, what kind of singularities we can find? This is, it seems to me that this is a very important question if we would like to have a structured theorem for this class of varieties. Right? Okay, my student Nancy, she tried hard. She was able to compute in different ways the Nash blow-up of the EIDS, and but she was able, for instance, to use methods of integral closure in order to try to detect pencils, exceptional lines in the fiber of the blow up. But in fact, she was not able to really see what are the type of singularities that we can find when we do the blow up of the EIDS. Recently, very recently, so in this very nice paper, and Phillips Krieger and Matthias Sack, they had been able to give some answers to that question using another modification. They didn't use the Nash. They used a modification that they called Trina modification, and which was used by Trina in her investigation of surfaces. And so let me come back here to my diagram. So the question is here, right? I mean, you can replace this resolution by another resolution. And then in a similar procedure, you can try to see whether you can factor that resolution to the EIDS and also to families of the EIDS. And well, they had been able to some extent to do this. And what they found is that under certain conditions, the Trina modification of the EIDS has local complete intersection isolated singularities. But they also proved that if certain condition does not hold, then perhaps this is not true. So you may have non-isolated singularities after the Trina modification, right? So, for instance, then they characterize a class of threefold Cohen-Macaulay codimension two singularities, whose Trina transformation only has isolated complete intersection singularities, as I said. Okay. So I was prepared to give a short explanation of what's the Trina modification, but probably if I do this, I will do this very quickly. I mean, because it's well, these constructions depends on looking in the right way to the generic determinantal variety and at the tangent space, right? So, and then in the case of the Trina transformation, what happens is the following. So suppose that you have a generic matrix in the set, so you look at this matrix as a linear map from, say, Cn to Cm, and then as A has rank t minus 1, then the row lines of the matrix, they determine an element in the convenient Grassmannian. So then we have a map from this set to the Grassmannian, in this case n minus t plus 1 n, right? And then I can look at the closure of the graph of this map to have my resolution in the space of the generic determinantal matrix. So I write W in MT as the closure of, so I have here, I didn't write the map, right? I didn't write the map. So for each A, I call here PA, exactly the map that gives me the kernel of the transformation, right? So then I write W in MT as the closure of the graph of this map. Let me put closure of the graph of this map. Sorry. So this is a set which lives here in MNN cross Grassmannian of n minus t plus 1 n. And we can see that the second projection of this map, of this product, defines the set as a fiber bundle over the basis, which is the Grassmannian, which shows that the set is smooth, right? And the first projection is exactly the resolution that I'm looking at. Okay. So this is the way we define the Trina resolution in the space of matrices, and then we again can pull back this to define the Trina transformation of the EIDS. Okay, so now with these two geometric constructions, the singular fibration and the Nash blow-up, or the Trina modification, we have some setting that led to some results that I will try to quickly recall. So, especially for the case of the isolated determinantal singularities which admit smooth. So what are recent results in this direction? Okay. So an isolated determinantal singularity admits smooth when n is less than n minus t plus 2, n minus t plus 2. So we know that determinantal varieties are Cohen-Macaulay singularities. And in this case of isolated singularities, they are the normal singularities. So we have the result of Groel-Steenbrink that gives that the first bit number of the generic fiber of X is 0. Right? And recently, Ballesteros, Orefsio Okamoto, and Tomasella, they got this Lie-Groel type formula, of course, using Morse theory and the setting that I just described, especially the first geometric transformation. If we look at the special case of surfaces, then we have only to consider the second batch number, as we know that the generic fiber of my varieties are connected and B1 is 0, so I just have to care about B2. And in this case, so the Milnor number was defined, the Milnor number of a determinantal surface singularity was defined as the second bit number of the generic fiber, which is, in this case, is a smooth. Okay? I'm sorry, let me say that this was independently defined in the treatises. Right? So, and also independently, they obtained a Lie-Groel type formula for the second bit number, which gives then the Milnor number of X plus the Milnor number of the x inter p inverse of 0 equals m2 of x, where m2 is that polar multiplicity I defined before, right? And which this, of course, corresponds to the number of Morse points of P in the generic fiber of X, which in this case is smooth. Okay. So, in her thesis, Miriam conjectured that for this class of singularities, so determinantal surfaces, singularities, this equality would hold. Mu of x plus 1 equals the Trina number of x. And using the geometric approach I described, she was able to work the normal forms of unfoldings, Krieger, and Neumann classification in too many examples. And this had been also completed with the examples done by Brian Pike. So putting together the classification, in fact, it was possible that the formula is true in the case of simple singularities, right? So, of course, it's a nice question to ask whether this is really true for all two-dimensional EIDS singularities. And here, I can make another remark, which is the following. Most results we get up to now, they are based on geometric constructions. And in fact, we need to search for formulas, algebraic formulas, which could give the invariants in terms of information on the X itself. Right? So this probably is a subject of Terry Gaffney's talk. Together with Rangachov, they use integral closure of pairs of models to try to give formulas for these invariants. Okay. Of course, this is new transparency. I gave this talk not long ago in Merida, and this is a new slide because this is really a very recent result of unfoldings Krieger. So we have now progress in the case of threefold singularities, which is the following. So in their investigation, Brian Pike and Jim Damon, in fact, they made a deep investigation of determinantal singularities, and they had been able, for instance, associating to the EIDS a tower of three divisors, they had been able to compute this number B2 minus B3 for the case of threefold singularities. But they had not been able to compute them separately. They thought that these numbers could be, that in fact B2 could be non-zero, right? But they had not been able to really realize that. And with the help of Trina transformation, Unfoldings Krieger and Matthias Sach, they had been able to compute these numbers for Cohen-Macaulay codimensional singularities such that the Trina modification has only isolated complete intersection singularities. Okay, so they found these numbers for singularities with this hypothesis. Okay, I have to finish, yeah. So, just to finish, I would like to mention the third construction, which is the sections. This is the easiest construction, but this is important fact here is that sections of isolated determinantal singularities, have good properties. So a hyperplane is a general hyperplane with respect to a determinantal singularity if it's not a limit of tangent hyperplane. But in our case, we just a little bit stronger definition. We would like sections that are transverse to all the strata of the stratification, because with this property, we obtain that the intersection of a good section with my determinantal variety is again a determinantal variety. Okay, unfortunately, I have to stop here and thank you very much. But let me just tell you that thanks. That I'm very sorry that I'm today more or less without energy because of my flu. But okay, thank you very much for your attention.